We have had a pleasant stay in Brighton so far. I'm Sven Kratz from the Harman Future Experience team, and my co-author is Tony Dunnigan from FXPAL. We're both based in California. And I'm happy to talk to you today about ThermoTouch, a new scalable hardware design for thermal displays. So what we set out to do is build an interactive display with a 2D addressable grid of thermal pixels. So that means we can, at certain pixel locations, provide hot or cold feedback for the user when he's touching the display. And we wanted it to be scalable, so enable a large surface area, more than a square meter, and also enable a large number of thermal pixels, so in the hundreds or thousands. Why did we think this is interesting? You have museums, increasingly using large touch displays, and I think it might be interesting to add a further output channel, in the form of thermal feedback, because, for example, in technical museums, there are lots of processes which you can show that involve temperature change, for example, a jet engine or a nuclear power plant. A bit, on a different track, you could imagine desktop AR games and adding, additional feedback that the user can feel on the desktop. We also looked at office spaces, so you could imagine augmented work desks with ambient notifications via thermal feedback, and all that, requires fairly large thermal displays, which we didn't have at the time, we still don't have. There's quite a bit of related work in this field. So one track of work goes into reproducing material sensations through temperature change, for example, Richter 2012. There's been a few works on using thermal feedback to display information, both in fixed locations, and Wilson also looked at using this for mobile devices. Halvey studied how different ambient conditions influence the perception of thermal feedback. And one prototype which is actually pretty close to this work is called ThermoPic Neo by Takada. And he built a grid of Peltier elements and also experimented with temperature, so thermochromatic ink displays. So you can see here when the temperature changes and the color of this ink changes. So there's a few issues we wanted to address with existing techniques. So many prototypes were single pixel, so we wanted a grid of pixels. And another thing is most of them are based on the Peltier element as a transducer. And it's actually a pretty useful component because it provides both heating and cooling depending on the polarity of the voltage you apply to it. It does need a complex driver circuit, so you need a H-bridge circuit, which you can see here in the bottom right, which requires at least 4 power transistors. At least for the cooling, it has a relatively high power consumption, and per unit it's quite expensive actually to buy. And you also only have discrete modules, so imagine building a 1,000-pixel display from discrete modules. So these are kind of impediments to scalability, so we wanted to think about a new concept or adapting existing technologies to enable scalability. So for a 2D thermal grid, we looked at, so what's the most simplest technique for heating? It could be like electric resistance. And liquid cooling has kind of been an established technique for cooling stuff down. So the way it works is you have a reservoir with coolant. This gets pumped through some kind of a chilling mechanism and goes to the place which you want to cool down, and then the warm coolant flows back to the reservoir. So it's actually a pretty simple system used in internal combustion engines up to nuclear power plants. The principles are always the same. This is another view of the prototype. So we have a PCB mounted on top of a manifold, and which gets cooled by coolant in the bottom, and we have inflow and outflow ports. So here on the right, you can see the arrangement we chose for this. Yeah, this came together as an initial prototype. So here you have the complete assembly of the PCB and the manifold. It's all bolted together with screws, and we have some gaskets to make it watertight. What's missing is we put a layer of thermally conductive silicone on top to enable top projection, so that we have a visual part. So in the paper, we go into some detail about the PCB design. So it's composed of an array of basically spirals of copper trace. And in the paper, we describe how to calculate the length to find the correct resistance. In the middle is the switching circuit. So it's actually a very, very simple circuit using one power transistor. So that's a quarter that we would need for a Peltier element. And here on the right, as you can see, the finished prototype of the PCB. So when this all comes together, it looks somewhat like this. So here on the left, you can see the prototype PCB put together. And as you can see on the bottom of this table is a lot of ancillary equipment, the pump and chiller and reservoir and lots of plumbing. So it was actually quite fun to put together. Might be streamlined in the future. Yeah, so it actually cold at the surface. So on the left, you can see it in a cold state, and on the right is a thermal image of an activated heater cell. So you can see the hot spot there. Yeah, once we've assembled this device, we need to know its characteristics. Can it kind of come close to a Peltier element? So that's kind of the goal. So first we looked at what input power do we put in, and what's the output temperature on the surface of the device. We chose a temperature range for evaluation for between 5 degrees Celsius and 70 degrees. So obviously in an interactive scenario you wouldn't want the user to touch a 70 degrees hot surface, but this is just for knowing the limits of what you can do with this device. Then we find a linear relationship between the power you put in and the temperature which is displayed, which is great for easy control. We also looked at maximum and minimum heating rate, maximum cooling rate and maximum heating rate. So the maximum cooling rate is about 3 degrees Celsius per second. Maximum heating rate is quite a bit higher, it's 21.4 degrees Celsius per second. And so how does this look in comparison to a kind of run-of-the-mill Peltier element, which you can get on several electronics hardware prototyping stores? It's the CP40236. We mounted it on a 1-inch aluminum block to act as a heatsink, because you need to get rid of excess heat from the Peltier element. We also found it has a linear relationship between input power and either cooling or heating. And so what is interesting for us is the energy consumption. So we can see for cooling, so for heating, it's actually more efficient than ThermoTouch, because obviously ThermoTouch is working against the cooling effect of the water. Although for cooling, in ThermoTouch we basically just turn off the device, and here the Peltier has to actively work. So here it is slightly less efficient. Cooling and heating rates compared. So for cooling, they're about the same. So the Peltier has a slight advantage. For heating up, ThermoTouch is much faster. So that was an interesting result. And yeah, what can you do with this? So we implemented a test application just to see, once we've put the device together, what it can do. So we thought about a thermal feedback system for video playback. So this enables an additional output channel for video. So you can, if you touch the device at a certain point, you can feel a temperature. I think this could for once be used for educational applications. So you can feel the components of thermal processes, and also you get a different experience of videos recorded with a thermal camera. And there are two ways of creating thermal video. So one variant was with a keyframe editor we developed. So basically, it's a web-based system, and the user can enter, for a given point in time, can enter the thermal output characteristics of the board, save that in a keyframe list, and then basically have the video annotated with thermal information. And the system will then automatically transition between these keyframes according to what the user entered. Also have another variant which is just easy to apply to video from thermal cameras. So basically it takes in the raw video feed from a thermal camera and converts this to thermal output on ThermoTouch. And this is just an algorithmic approach. And more details in the paper. I won't go into depth here. One key component which is missing is how to actually change temperatures from one value to another. We chose open loop control for simplicity, and because we have this linear mapping function, so we actually know which power to set for a given temperature. However, it's very slow to just switch from, so if you're switching from 20 to 30 degrees Celsius, just switching to the different voltages which correspond to the output temperature. Actually, what we want is to change the temperature at the maximum rate. So what we did is find out the maximum heating and cooling rate, and use full power for heating and 0 power for cooling. And then we can determine the time interval required for full power or 0 power to affect the temperature change as fast as possible. So basically result in these kind of power profile functions you see on the right.
Firing chain is armed.
Yes, this is kind of a small demo.
Pressure water system is being activated.
You can see the thermal output on the top left.
10 seconds, go for main engine start. 7, 6, 5, 3 engines up and burning. 3, 2, 1, and liftoff of Space Shuttle Discovery.
It starts to warm up.
To the moon, Mars, and beyond. And the vehicle has cleared the tower.
You see it's really red hot.
All systems remain go for Discovery. Altitude now 9 miles, 6 miles.
And this is the automated variant, so it is just directly taken from the thermal video and output as with thermal feedback. So just to discuss, so at the beginning I mentioned we can also use closed loop thermal control, which might be better but more complex. So you would have to add a temperature sensor on each thermal pixel, but it might help compensate for fluctuations in the coolant temperature and make it more robust in general. I still owe you actually a large-scale prototype. I claim this is good for large-scale prototypes, so this still needs to be realized. So to discuss the liquid cooling system, there's obviously a low constant power demand, so you have to keep the chiller unit running all the time. However, you don't need to put much power into this because the coolant itself has lots of thermal capacity, and so peaks in thermal demand are bridged actually by the capacity of the coolant. And this approach can also be used for Peltier-based systems, so it's not exclusive to resistive heating. And obviously the cooling system will have to scale with the size of the thermal display. What we did see is another problem is the heating efficiency. So you can see it's working against the coolant, so we actually have to put in more heat energy than necessary. However, there are some workarounds around this, so you do not need to heat the entire board all the time. You could use a camera and see where the user is touching and then just heat the area surrounding the touch and just leave the rest of the PCB switched off. But still, I believe that large-scale resistive heating grids can be cheaper than lots of Peltier elements. So for one, they can be printed, so you can print the manifolds with 3D printer. You can print the PCB on different substrates and make this really cheap and very large. And you only need 1/4 of the resistors. So with that, I would like to thank you your attention. And I'd like to give a shout out to Tony, who's been very great at doing all the visual assets for this work. So thank you very much.
Thank you very much. Are there any questions?
Thank you. Can you talk about the actual numbers or how much does it take to build the prototype? I mean, how much money would it be that you would need to build such type of prototype?
Well, it depends if it's a one-off or you know, if you go into mass production. But I don't know the exact number. I would say the ballpark. So the most expensive part was the power supply, which costs $300. So it's a high power supply. But for any large system, you would need a strong power supply. So maybe $1,000 went into the hardware. Yeah.
Could you maybe improve the cooling performance, because that's where it is going a bit lower, just like they do with computers, like underneath the PCB, have some aluminium ridges, have a faster flow, so that you have more surface and more flow across the surface?
Yes, that's a great suggestion, because this PCB was just a normal PCB from a PCB fab, so there's no modification. So you could add more like a thicker copper layer, solder on cooling fins, like try to put it on a different substrate, not this fiberglass, because I think that insulates also a little bit. So yeah, great suggestion. Yeah.
I have a question about, since I don't know anything about thermal displays, can you leave something on, can you leave the heat on in a certain spot for long periods of time?
Yes, I think so. You apply. The system uses pulse width modulation to apply heat. So it's basically a dynamic voltage setting which you can apply to each thermal cell. If you don't leave it at max power, then you can leave it on indefinitely. Max power would burn out the cell at some point. So. Yeah.
When you were showing the demos, I was immediately thinking, this might be a very interesting way to serve visually impaired people using touch displays.
Right.
So basically heating where a button is or things like that. So has anyone ever looked at anything like that?
Not to my knowledge right now, no. But certainly, yeah.
Are there any other questions? Okay, let's thank the speaker. Thank you very much.
Thank you.